Introduction. Object recognition is a fundamental problem in computer vision and architectural intelligence that involves identifying and locating objects within digital image or videos. This technology has numerous applications across various domains, including autonomous vehicles, robotics, surveillance systems, augmented reality, and many others. The ability to accurately recognize objects is a critical component of developing intelligent systems that can intercept and understanding the surroundings. In recent years, significant advances have been made in object recognition due to the development of deep learning and convolutional neural networks. These techniques are revolutionized in field, enabling more accurate and robust object recognition system. However, object recognition remains challenging task due to the complexity and variability of real-world objects and occlusion lighting condition and viewing changes. This research paper aims to provide a comprehensive overview to object recognition in artificial intelligence. It will cover the fundamentals, concept, techniques, and algorithms used in object recognition as well as discuss the various types and applications to technology. The paper will also explore current state-of-the-art methods and future research directional in this field. How object recognition works. Object recognition typically involves several stages, beginning with the acquisition of an image video feed. The acquired data then processed, enhance it, and remove any noise and enhance artifacts. This step is crucial and significant impact in performance to the subsequent stages. Pre-processing techniques may include operations such as image sizing, contrast enhancement, noise removal, and color normalization. These operations aim to improve the quality of input data, facilitate better feature extraction next stage. Features extraction. Once the input data has been processed, the next step is to extract relevant visual features from the image or video frames. Features sample is a critical component of recognition as it determines the distinctive information that will be used for object representation and classification. Traditional features extraction methods include techniques such as edge detection, corner detection, and descriptor computation. These methods rely on manual design algorithms to extract low-level features like edge, corners, and gradients, which can be used to describe the local and global characteristics of objects. However, with the advent of deep learning, feature extracting has been more automated and data-driven. Convolution-neutral networks has emerged powerful to for learning hierarchical features and representations directly from raw image data. Low-level features for high-level representation that capture complex pattern and semantic information. Object representation and classification. Once the relevant features have been extracted, the next step is to represent the classified object based on these features. This involves comparing the extract features against database of object models templates using regular algorithms. Traditional object and recognition methods often rely on techniques such as template matching, features matching, and classical matching. Algorithms and support vector machines or decide trees. Methods compare extract features against set predefined object templates or models, and classify the object based on similarity or dissimilarity of the features. In recent years, deep learning techniques, particularly convolutional neural networks, have become the dominant approach of representing classification. During training, are presented with a large database of image where image is associated with a specific object class. The network learns to map the input image corresponding object classes by adjusting the internal parameters through a process called backpropagation. Once trained, the CNN can be used to classify new unseen image by propagating the input through the network and obtaining predicted object class based on the learning representation.
Object detection may sound like a pinnacle in artificial intelligence, but it coexists with us in our lives. Hiding in plain sight, we often fail to notice simple applications of object detection around us. Have you ever wondered how a face unlock works on your smartphone? Or how a self-driving car operates on its own? The answer is object detection. So what is object detection? Technically, object detection is a technology that includes computer vision and image processing used to detect objects in images or videos. Sounds interesting? Let's break it down for you using a simple example. Self-driving cars make use of the moving object detection technology where computer vision and image processing are used to determine the distance between the car and the moving objects to create alerts and guide the self-driving cars. You must be wondering, what is the technology behind it? Well, artificial intelligence is the basic principle that drives object detection. The idea is simple. The data is collected through computer vision. The data is then fed into the model, and using machine learning algorithms or deep learning algorithms, conclusions are made. The camera collects the image from different angles and sends it to the image processing unit. Now, based on how the model was trained and what the training data was, the results are laid out to the system in the form of alerts or instructions like how far the object is, if the object is moving, or if the object has stopped. Object detection has also been paving a glorious path for the surveillance industry. Traffic tracking systems, activity recognition, even sentiment analysis through object detection are all possible now. Surveillance has picked up a lot of pace with object detection. With increasing efficiency in object detection technology, it is evident that artificial intelligence is on the rise, and it will eventually create a lot of job opportunities in the coming years as well. Edureka's postgraduate program in AI/ML, in collaboration with NIT Warangal, will help you in mastering such advanced AI concepts with the help of experienced mentorship and placement assistance. Sign up today to become the leaders of tomorrow.
Types of object recognition. Object recognition can be categorized into various types based on specific problem being addressed and the techniques employed. Some of the most common types include: number 1, instance recognition. Instance recognition focusing on identifying specific instances of objects, such as recognizing a particular individual's face or a specific car model. These types of recognition is often used in applications such as biometric authentication, surveillance, and vehicle tracking. In instance recognition, the goal is to make the input image or video frame against a set of known object instances stored in a database. This can be achieved using techniques such as template matching, feature matching, or deep learning-based classification models trained on specific object instances. Number 2, category recognition. Category recognition involves identifying objects based on their general category or class, such as distinguishing between different types of animals, vehicles, or furniture. These types of recognition is useful in a wide range of applications, including image and video understanding, robotics, and content-based image retrieval. Category recognition algorithms typically employ deep learning techniques such as convolutional neural networks to learn the visual features of patterns that distinguish different object categories. These models are trained on large data sets containing labeled examples of various object categories, allow them to generalize and recognize new instances of those categories. Number 3, semantic segmentation. Semantic segmentation combines object recognition and pixel-level segmentation to identify and delineate the boundaries of different objects within an image or video. This type of recognition is particularly useful in applications like autonomous driving, medical imaging, scenes understanding. In semantic segmentation, each pixel in the input image or video frame is assigned a class label corresponding to the object it belongs to. This allows for precise delineations of objects' boundaries and provide a detailed understanding of the scene's compositions. Semantic segmentation algorithms often employ fully convolutional neural networks or encoder-decoder architectures, which can efficiently process and segment entire image in a single pass. This model learned to map input image to dense pixel-wise predictions, assigning each pixel a class level corresponding to the object it belongs to. Object detection. Object detection extends object recognition by not only identifying objects, but also locating their positions within the image or video frame. This is achieved by drawing bounding boxes around the detected objects, providing information about their location, size, and aspect ratio. Object detection algorithms combine object classification and localization techniques into a unified framework. Early approaches such as a sliding window detectors and deformable part models relied on handcrafted features and classifiers. However, more recent methods such as region-based convolutional neural networks and their variants leverage the power of deep learning to perform object detection in an end-to-end manner. These algorithms first generate a set of region proposals and then classify and refine the location of these proposed region using a convolutional neural network. Instance segmentation. Instance segmentation is a more advanced form of object recognition that combines object detection and semantic segmentation. It not only identifies and locates objects, but also delineates the precise boundaries of each individual instance of an object within the image or video. In contrast to semantic segmentation, which assign a class label to each pixel, instance segmentation further distinguishes between different instances of the same object class. This is particularly useful in scenarios where multiple instances of the same object types are present, such as counting and tracking individual or vehicles in the scene. Instance segmentation algorithms typically employ a two-stage approach where object proposals are first generated, and then a separate segmentation head is used to predict instance-level segmentation masks for each detected object. These algorithms often leverage the power of convolutional neural networks and techniques like region proposal networks and mask prediction branches to achieve accurate instance-level segmentation.
In today's artificial intelligence class, we will see the object recognition by appearance from fourth unit perception. And in today's class, we will see the object appearance, how the object is appeared in an image, and then classifier, what is the role of classifier, and then how the classifier is used to detect the face, that is face detection. After that we will see the two subtopics from this object recognition. The first one is complex appearance and pattern elements, and second one is pedestrian detection with hawk feature. Pedestrians means the people who are walking on the road. Okay, so this is pedestrian detection with hawk features. Let us see all those things one by one. Object recognition. Object recognition is a software program which allows to identify the object from the still images, right? So that the method used to identify the objects, which includes 3D models, component identification, edge detection, and analysis of appearance from different angles. So these are the methods which are used to identify a particular object from a still image. Object appearance. Here the appearance means how the object looks like in an image. Okay, this is called as appearance. So based on the appearance we can divide the objects into two different categories. First one is some objects, the variations are very little. Okay, for example we can take baseballs or any other balls. The ball's shape will be very similar. The difference will be very little when come to the ball. Okay, this is the first category. When come to second category, the variation are very different. Very high variation will be there. First one is house. So we are having so many different types of house. So it varies based on size, color, shape, and the house can be looks different from different angles even. Okay, so the variation is very great here. And second one is ballet dancer. So while dancing the pose will be changed differently, and based on the stage light and color also the object, that is the dancer, will looks different. Okay, so in these cases we have to compute the feature of a particular object. So based on the feature we have to classify the images by using a very good classifier. Some other objects are there which are having their own local patterns. So with this local pattern, it is very difficult to detect some part of the particular object. Okay, by using the local histogram of detector response, we have to identify the part of particular object. For example, here the bird is having its own pattern. To identify the eye, we don't know whether this is a part or a pattern, local pattern. Okay, so here we have to fix the features of this particular object. Based on the feature we have to identify. For that a very well trained classifier is required. The classifier is an AI algorithm which maps the input data to predefined categories, and it is used to make the process easier for the user, right? And the classifier will analyze the data automatically, and it simplifies the operations and obtain useful information. Here we are having a patient's medical data. From this data the classifier model will classify the patients who are having diabetes and non-diabetes patients. Okay, so by using the classifier we can easily classify the patients with a different set of classes. And next let us see how the classifier is used to detect the faces. That is, the classifier is a very good option for face detection, and the classifier works extremely well when the face looking directly at the camera. Okay, if the face directly see the camera, then it will work extremely good, because at low resolution under reasonable lighting in all such faces looks quite similar. Okay, all the faces are round in shape. Okay, see, round in shape, and all the face are having eyes. Eyes are dark in color, and the mouth is also somewhat dark when compared to face. And the eyebrows are also somewhat dark when compared to the other face area, and every face is having its own nose. So this is the nose. So if a face is there means this is the face. In this face there should be two eyes. See these two eyes and mouth area and nose area. Okay, so to identify the face is very easy. The very big challenge is illumination here. Okay, so the illumination causes some variations in this pattern, but these variations are manageable, right? So the classifier will easily identify the faces in the images. Here we sweep a round window to fixed size over the images. Okay, for example, the orange square is the size of face and the green square is the size of eyes, and this yellow square is the size of mouth. Okay, the maximum size of mouth. Okay, by using those windows we can extract the features of the object. Okay, how the object is appeared in the image. Okay, so this rounded window which is called as sliding window. So what is the purpose of sliding window? Sliding window is very much helpful for extracting features from the image. So based on the illumination and its direction, that is illumination direction, the face features may be changed, right? Because uh, based on the illumination, the shadows may appear on our face, hence extracting features will be somewhat difficult. Here two strategies are there. First one, to build features out of gradient orientation, and second one, to estimate and correct the illumination in each image window, right? So we have to correct the illumination, then only the features may be extracted correctly, properly, right? To find the faces of different size. Okay, see we are having different size of faces. To find the different size, repeat the sweep over large or smaller version of the images. So based on the size, the sweep will be varied, right? And finally, the post process the response across scale and locations. So based on the location, the scale will be varied. So if the object appeared nearer, then the scale will be large. If the object is very far, then scale will be small. Okay, and finally we will find the final set of deductions, that is deducting the features. Okay, here by using this procedure we have several overlapping windows that each report a match for a face. Okay, each window is used to represent a face. And this is the architecture of face finding system. There are two parts, first part and this is the second part. Okay, in the first part original image is there, and that is given to non-maximal suppressions to detect the faces, that is the location of faces in the image. That is the first part. When come to second part, sweep the windows over the large and smaller version of the image. Okay, so this is the large version and this is the smaller version, the face. Okay, smaller version of images, so that we can find the small or large faces respectively. Okay, the illumination in the window is corrected. Okay, correct the illumination, right? And estimate the orientation, rotate window, and features will be extracted, and then that will be given to classifier, right? Here the output of classifier is post processed to ensure that only face is placed at each location in the image. Okay, so each window should contain exactly the face. So this is the face finding system architecture. And there are two subtopics in object recognition by appearance. First one is complex appearance and pattern elements, and second one is pedestrian deduction with HOG, that is hog features. The first one is complex appearance and pattern elements. Okay, when compared to faces, many objects can produce more complex patterns. So based on the view of a particular object, the shape of the object will get changed. So based on that, the first one is foreshortening, and second one is aspect, third one is occlusion, and fourth one is deformation. Right? Foreshortening. Foreshortening means the same object may be seen in different direction, then the shape will get changed. That is, the circle will be viewed as ellipse if we see the circle in different angle. Okay, the angle will get changed here. So the second one is aspect. Aspect means, so if we see the same donut in different direction, then the shape of the donut get changed. Okay, that is, if we view the same object from different direction, then the shape of the object will get changed. Okay, this is the second one, and third one is rotation. That means this is the mug. If we see the mug in this direction, then we can see the handle of this mug. Suppose if we see the same mug in this direction, then the handle will get disappeared here, right? And fourth one is deformation. Deformation means time to time the shape of the object will get changed. Okay, first time the shape will be like this, and after some time the same object will be seen in this form, right? So the object can deform dramatically time to time. Hence the effects like the foreshortening, aspect, occlusion and deformation. So the effects can move the features around the image of an object, right? So the role of object recognizer, the role of object recognizer is to collect these features of an object and then find the pattern elements, to find the pattern elements, whether those elements are appeared in right place in the image or not. So accordingly the object recognizer can recognize a particular object in an image. The next one is pedestrian deduction with hog features. Pedestrian means the people who are walking on the road. So it is important to deduct the people who are walking on the road, because per year the car accident alone kills about 1.2 million people, in which two-thirds of people are the pedestrians, that is the people who are walking on the road simply. And it is important to fix the pedestrian detector in a car to protect the people who are walking on the road, and it will save many lives. The pedestrians wear many different types of clothing, and the configuration also looks different, right? See, in this diagram the people are wearing different types of clothes and their shape also be different. Okay, and the resolution is also very low here. And now we need to identify a pedestrian. So there are two normal shapes. The first one is lollipop shape if they are standing one side of the road. Okay, and the shape can be changed to scissor like shape if they are walking on the road. Okay, now it is important to extract the important features of the pedestrian. So like the arms, legs, and the curved shoulders and head. So these are expected features to extract from the image. Okay, so with the careful feature construction, we can build a useful moving window pedestrian detector. Okay, moving window pedestrian detector. There should be a strong contrast between the pedestrian and the background, so that we can easily detect the pedestrians from the background, right? So for this we can use the orientation to represent the image window, right? So by using image window we can detect the pedestrian, right? And in this image window the pedestrian can move their legs and arms and here we should not worry about the facial features of the pedestrian. So for this, the facial detection is not required here. For that, the window will be splitted into small cells and that should be overlapped and build an orientation histogram in each cell, right? And this will produce a feature that the head and shoulder curve is at top of the window. See, head and this is the shoulder. Head and shoulder should be placed in the top of the window, but the head can move slightly and the head should not come to the bottom of the window, right? So building the pedestrian detection is also like building face detector. Here the detector sweeps a window across the image. Okay, see, like windows are there across the image and the compute features for that window and then present it to the classifier, right? And the non-maximum suppression which needs to apply to the output, right? Here, in most applications, the scale and orientation of pedestrian is known, right? So, if the object is near, that is the pedestrian are close to the car, then the size will be very large, and they appeared very long distance means the size will be very less. That means in driving application, camera is fixed into the car and they can view many vertical pedestrians, okay, vertical pedestrians, and they are concentrated only the nearby pedestrians, right? And now several pedestrian data sets are already published which are available in the internet, and those data, that is those data set can be used to train the classifier. By using those classifier we can build our own application to detect the pedestrians. So far we have seen the object recognition by appearance from fourth unit perception, and in this class we have seen the object appearance, classifier, face detection, complex appearance and pattern elements, and finally we have seen the pedestrian detection with the hub feature. That is, the same classifier can be used for face detection as well as we can use the classifier for detecting the pedestrians also. And in the next class we will see another important topic from fourth unit. Thank you.